In this chapter, we will see some common applications of linear programming in economic enterprises. The first application is in regards to the maximization of profits for a farmer. Here, the farmer needs to choose which crops to plant in the land. The objective is to maximize profits given the net revenue from planting each crop, subject to three common conditions: capital, labor, and land. In the objective, the decision variable is the amount of acres that we will plant from each crop. This choice depends on the net revenue received from each crop. Notice that the net revenue depends on the revenue from the enterprise minus the cost. The revenue is price times quantity, where the price is dictated by the market and the quantity is given by the productivity of the land. The cost is mainly driven by the variable cost per unit of land. In the constraint, we have the following general formulation for each of the resources. For example, here we have labor constraint. U1 represents, for example, the amount of labor in hours needed to produce 1 acre of corn. U2 will then represent the quantity of labor in hours needed to plant 1 acre of soybeans. L will be then the total amount of labor that is available. Notice that we need to be careful with the units. Sometimes revenue can be based on production, whereas land and labor constraints are based on total land used, not in total production. Therefore, we need to ensure that every variable have the same units before solving this problem. Let's illustrate these concepts using the following example. Here the farmer can choose between two crops, corn and soybeans. She has 450 acres available. We have the productivity of an acre of land in terms of corn and soybeans. We also have the variable cost from plowing, disking, planting, and harvesting an acre in terms of the cost for corn and the cost for soybeans. We also have the expected price for each crop in dollars per ton. We have the total available number of hours of labor and the requirements for corn and soybeans in terms of labor. In addition, we also know the quantity of working capital that the farmer has. Our task is to formulate this problem as a linear programming problem. We need to define the notation and indicate the units of all variables and equations. Then we will use Solver to solve this linear programming problem. Let's start with the objective function. Here, our intention is to maximize the profit of the farmer given two crops, corn and soybeans. Here, the decision variables are the acres of corn and soybean planted. Therefore, the revenue must be also in dollars per acre. Revenue per acre is equals to the price per unit times the yield. According to the data, the price per unit was $120 per ton for the case of corn. We multiplied that by the yield, which was 2.7 tons per acre. Notice that here we can cancel tons and our result is in dollars per acre, which coincides with the units of the decision variable. In the case of cost, notice that is already given in dollars per acre, therefore we do not need to proceed with any further step. Then the total net revenue is simply the revenue per acre minus the cost per acre times the number of acres. For the case of corn is 324 minus 30. For the case of soybeans is 432 minus 45. In both cases, we will obtain dollars per acre times acre. Therefore, the final units will be only in dollars. This results in this objective function. 294 is the net revenue per acre of corn and 387 is the revenue per acre of soybean. Now let's proceed with the structural constraints. From the problem, the total amount of land is 450. This means that the quantity of acres planted for corn and soybeans must not exceed 450. In terms of capital, the total working capital was $30,000. Corn requires, in terms of capital, $30 per acre, whereas soybeans requires $45 per acre. In terms of labor, the family has 15,000 hours available. Corn requires 40 hours per acre, whereas soybeans requires 60 hours per acre. This results in the following linear programming problem. Now let's implement it in Solver. As you can see, I used a similar formulation as in the previous cases. For the objective function, I put first the coefficients, then I left in blank 3 cells, one for the objective function, which is the profit, and 2 for each decision variables, the first one for corn and the second one for soybeans. Subject to 3 constraints, notice that I indicated the units and the coefficients. For example, for the first constraint, both are equals to 1. For the second one are 30 and 45, and for the third one, 40 and 60. We leave in blank one cell for each constraint, and then we indicate the signs and the limits. Now let's proceed to implement the objective function. Remember that is the multiplication of each coefficient with its respective variable. So we can do that by using the formula sum product. We select the coefficients, comma, the objective value, and we close. The value right now is 0 because there are no optimal values. We do something similar for each of the constraints. We multiply the coefficients of the first constraint with the optimal values. Because we will use the same cells for the optimal values, we can use the $sign to block these cells. In that way, we can copy and paste 2 more times the formula, and as you can see, it works properly. For example, for the third constraint, it selects the coefficients of labor and multiply with the optimal values. Now let's go to data and select solver. Here our objective is located in D3. We want to maximize it by using the decision variables that are located in these two cells, C7 and D7. Then we add the constraints. We select the blue cell, we check that the sign is correct, and then we select the limit. We proceed in the same way for the other two constraints. And we press OK. Then we need to be sure that this is checked, because this ensures that the variables are non-negative, and we select simplex and we solve it. Here we select sensitivity and we press OK. Solver found an optimal solution. Notice that according to the system, it is recommended to only plant corn, and this will provide this potential profit. Notice that here the restriction that was active was the quantity of labor. Notice in the sensitivity report that this is correct, because labor is the only one that has a shadow price. Because the sign is less or equal than, and this is a maximization problem, this means that increasing one more hour of labor could potentially increase the total profit by $7.35. This is an important valuable information because, for example, if we know that potentially increasing 1 hour of labor can provide $7.35 more, this means that depending on the state, we could hire actually labor and still get profits. For example, if the minimum wage for agricultural labor is 7.25, for example, in Indiana, this means that we could still gain 0.1 for each extra hour of labor. But for example, if we compare it with the minimum wage in Florida, which is currently about 8.46, then this would not recommend to hire more labor, because we could actually lose money, because 7.35 is less than 8.46. In that sense, you can see that using solver and linear programming can have important implications when taking the decision of hiring more labor, especially the shadow price, as you saw. Because if the shadow price, which tells you how much profit you can obtain by increasing, for example, the quantity of labor, is higher than the wage that you will pay for an extra amount of labor, then you can actually hire more. In addition, linear programming provides you with flexibility. For example, you could add many other conditions that can help you to test other details, such as renting additional amount of land. But for example, here, you would not need more land because actually you would use only 375 acres. But this is less than the amount of land that you have. Therefore, here, for example, tells you that you do not need to rent extra land. And on the other hand, here you can see that if you use only this amount of money, then you do not need this quantity of working capital. And in that sense, that could tell you to reduce the capital that you could ask, for example, to the bank, and actually devote more effort to increase your labor. So as you can see, linear programming can provide you with several insights depending on the problem and the scenario.